Welcome back to INST 314, Statistics for Information Science. I'm your host, Shawn Janzen, and we're continuing our talk on the Inference Part 3 module, Normal Distribution, Z-Scores, and Confidence Intervals, into Topic 7.3, looking specifically at Z-Scores. In the last video, I left you off with asking a question about how we could compare a couple different midterms, and that we would need a tool called Z-Scores to help us figure that out. So let's go ahead and learn to calculate Z-Scores in this particular video. Now, Z-scores, first of all, takes a baseline that our data are normally distributed and that these values can be converted into a Z-score. You calculate a Z-score by taking the particular value you're looking at minus a mean divided by a standard deviation. And so we can look at it in a formula perspective of x, where x is your observation value, minus mu divided by sigma, if we're dealing with population data, or x sub I for the individual value, minus x bar as the mean, divided by s, the sample standard deviation. And the z-score is a standardized distance from the mean. When we divide it by a standard deviation, we are standardizing our value. So we're stripping away any particular value labels it might have, like the number of pounds or the number of miles or the number of dogs someone might have. And so in this case, it's just a standard metric. It centers the mean at 0, and we are seeing how far is this z-score from that centered value of 0. And once we deal with that, we can use it to find out what's the probability of finding that z-score, and we can compare it with other z-scores from other groups. It doesn't matter where this data came from originally, if it was the number of dogs or the number of gold carrots in a watch. A z-score is a z-score, and you can compare them across. Now, when we're using this normal curve with z-scores, we first compute the z-score. So you change that raw score into that standardized value of z, and you can use it when you know the standard deviation is known, and you have to have a sample size of at least 30. The more skew you have in the data, you can still do with it, but you have to have a larger sample size. And there's no real hard rule of how large of a sample size you need. Just know that the more skew you have, the larger the sample size you need, and we'll wing it from there. So going back to our example in the previous video, which exam score was better, we said that the first midterm score was distributed with a mean of 60 and a standard deviation of 6. And the second midterm exam was normally distributed with a mean of 80 and a standard deviation of 4. Now, on the first midterm exam, we scored a 68 and an 86 on the second midterm. Which one did we do better on? So we can figure that out. The z-score of the first midterm is our score of 68 minus the class average of 60 divided by the class's standard deviation of 6. And when we do the math, that comes out to a z-score of 1.33. But on the second midterm, we had a score of 86. We subtract that from the class mean of 80 and divide it by the class standard deviation of 4. And that gives us a second midterm score z of 1.5. So on its general face, we can go ahead and say, since these are distances from the mean, the z-score that is farther from the mean as a standardized value is going to be the better score in this case. So 1.5 is larger than 1.33, so we did relatively better on midterm 2. Now, when we're looking in R, and we can go ahead and we can be a little bit more precise. What we were doing before was just by hand calculators or stuff, and we lose decimals and things like this. So we can use R to generate z-scores for us and give us a little bit more precision here. And what we're going to do is we're going to use the p-norm function. That's P-N-O-R-M. And inside this, you put in the statistic that you're looking at. So in this case, the first one is our test score of 68, comma, mean equals, and we specify the class mean was 60, comma, SD equals, and we enter in the class standard deviation. And that's going to say, what's the probability of getting a score up to 68? Remember, this is a curve. We're going to start from the farthest most left tail, and we're going to count probabilities going all the way up. And it says you're going to get into the 0.909 rounded percentile or probability of getting that score of 8, right? So you're doing pretty well. But if we did the p-norm on 86 with a mean of 80 and SD of 4, then you are getting a 0.933, which then, if we translate this out, is that you did better than 90.9% of people in the class on the first midterm, but in the second midterm, you did better than 93.3%. Right? That's where we're getting back into those percentiles and things like that, although it's expressed as a probability now, but multiply it by 100 and you're there. So p-norm, like I said, is going to get you to the probability score of finding that particular z. And we can also use a z-table to find areas below a score. you've already been introduced to a chi-square critical table. Z-scores are a little like that, but we read them differently. So the critical region is referred to as the area under the curve. It's not a critical value, it's a probability under the curve on a z-table. And we use a z-table to find the areas above and below the z-score. So think of a normal curve, shade in the area that you're interested using the z-score, and then take note of which side the sign is on, and we'll go ahead and dig into it. So on the screen, I have a snapshot here of a z-table on the negative side. And the way we read z-scores is that we take the left side or right, depending on how your book is presenting it, and it'll say like a negative, we'll say for example 3.4, and that says it's the ones position, period, first decimal or the tenths position, and that's in the column on the left or the right side. And then up across the top we have the second decimal point of the z. So what will come after that negative 3.4? Then you might have a 9 or a 0.8, and so that's that second decimal, and we intersect those to find the probability under the curve. This other half here, this is the positive z-score side, and so this is everything above 50% because that middle value is halfway under the curve, so that's 50%. And it's that same concept. The column on the left indicates where we are starting with the ones and the tenths position after the decimal, and then the columns are the hundredths position after the decimal. And when we want to go ahead and look at these probabilities, these are all probabilities on the table here. They go from 0 to 1. So the higher the value, the more likely you're going to get a particular probability. So let's go ahead and use these z-tables to figure out the probability. If we have a distribution with a mean of 13 and a standard deviation of 4, what's the probability of randomly selecting a score of 19 or more? Keep an eye on the or more part. So first let's go ahead and find out its z-score. So we have our score of 19 minus our mean of 13 divided by standard deviation of 4 gives us a z-score of 1.5. So we can go ahead and go into a z-table, and I've brought up a snapshot here, zoomed in on a z-score here, and we are going to go ahead and locate 1.50. Our z-score is 1.5, but if we add on the hundredths point, that second decimal, so we can be more accurate when we look at the z-table, it's 1.50. So we go down the first column there, find the 1.5, and then we move across the columns to the 0 in the second decimal spot. And that tells us we have a probability of getting a z-score of 1.50 is 0.9332. That's the probability of going from the left tail all the way over towards the right. Now, this may seem a little familiar to you because we also said in just the example before where we were comparing some test scores that we had a z-score of 1.5 and also had a probability of 0.933. This is where that 0.933 comes from with the p-norm function that it's working on. Now, I had also said that we wanted to know the probability of finding a z-score of more than 19 or more. So in that case, we want to know the probability on the right side of the curve that's not under that shaded region in the graphic here. So in this case, we take 1, which is the maximum value under the curve, minus the probability we found. So 1 minus 0.9322. And we go ahead and see that it's 0.0668, or approximately 6.7%. So how can we go ahead and calculate a z-score in R? Well, I don't have a nice easy formula for you like the p-norm, but what you could do is it's fairly straightforward just to kind of use it like a calculator. So we can go ahead and put in parentheses x minus the mean of x, where x is some vector of data that we have saved, divided by the standard deviation of x. And that will go ahead, we can assign it into z. And so if I show you an example here, we could use z as 19 minus 13 divided by 4, putting in some parentheses around the 19 minus 13 to keep the order of operations intact, and that tells us 1.5. Of course, you don't have to assign it into a letter like z. You could just run the math as the calculator, and it'll tell you 1.5. I had just saved it as z in case I want to use it later, like we're going to see when we get to confidence intervals. Now, also, we were saying that you can use p-norm to find the probability of the left side. If you do 1 minus p-norm, that's going to tell you the probability on the right side, like we were saying, a score of 19 or more. And an alternate approach, if you don't really care if you're looking to the left tail or the right tail, we can use a p-norm, put ABS, which is short for absolute value function. So if we wrap our value z in ABS and put that inside p-norm and indicate lower tail equals false, this will always go ahead and tell us the probability of finding that score underneath the tail, regardless of which tail it is that we're looking at, for the left or the right. Neat little trick. So can we go ahead and reverse this? And if we have a probability, can we get the z-score? Yes. So in this case, you may remember if we were working on the chi-squares, you had q chi-square to get the chi-square critical value. Well, similarly, we're going to have a q in front of norm to get a z value. So we're going to do q norm on a given probability for a one-tail value. And if we do an absolute value of q norm probability, then we're going to get the probability of the one tail for the right tail. So also then we can do q norm probability divided by 2 for a two-tail. Well, keep in mind, when we're doing these two-tail tests, we could look in either particular direction, and so we would do the probability divided by 2. So if we wanted to find out what was the score, we said before, of getting a 19 or more, and we're looking in that right tail because we wanted to get the high-end value, we would do an absolute value of q norm on the probability we had of 0.0668072. I just took the whole number to make sure we were as accurate as possible, and it says it gives us a 1.5, which is the z-score we had from before. So let's go ahead and talk briefly about determining normality here. We said before that we have some features about normal distributions, and we can go ahead and eyeball it real quick. We can use tools like histograms. We can also use something called a quantile plot, also called a QQ plot, also known as a normal probability plot. Let's go ahead and take a look at a few. So on the visual on the left is a histogram, and we've overlaid a curve on top of it to kind of a normal curve to kind of see how well does it match underneath this normal distribution. And on the right, we have what's called a QQ plot. And a QQ plot puts the theoretical z-scores you should get on the x-axis and the observed scores that you get on the y-axis. And when your theoretical matches up with what you would observe to find, then they overlap each other. Well, they don't overlap, but they meet each other on the graphic where we have this black bisecting line cutting through the plot. And if all of your values, the observed, meet up with where they should theoretically be, then they match along that black line perfectly and very tightly, and you are normally distributed. But the more your dots deviate from that black line in a QQ plot, the less normal your data is. And the readings will go into a little bit more in terms of reading these QQ plots and finding out when they deviate to the top or the bottom where that skew is in particular. We can go ahead and look at this last one here and see different versions where we have different degrees of normality as well. So the blue one, we have 3 different histograms. The blue one looks relatively normally distributed, but when we put it in the QQ plot, we see we've got some noise, that it's bouncing around a little bit as we get down to the lower left, and it's coming up a little bit in the upper right. The green one also looks normally distributed, but our QQ plot here shows that we have also some disruption on the lower end and the upper end, with a few outliers starting to pop up on the upper part of that distribution as well. But if we look at the one in yellow, it also looks normally distributed with a histogram, but the QQ plot shows that it's very tight along that dotted line there. So histograms, don't treat them as your final test. QQ plots will always be more accurate than histograms alone. And with that, I'm going to go ahead and see you in the next video.